All right. Hi, everyone. My name's Nick. I'm from Carnegie Mellon University, and I'm the session chair for this first poster spotlight session. We're going to make up some time. So we're going to stick to 2 minutes per talk. I think it's best if I hang out up here. I'll be navigating through the slides. So for all of our remote presenters, if you could just give me a cue when you want me to move forward. I'll be running a timer for 2 minutes each. I spotted the camera there, so I will give a non-verbal cue with 15 seconds left and then an alarm when 2 minutes is up. And so I think we have 8 talks to go through and then lunch. So without further ado, the first talk is Quasi-Bayesian nonparametric density estimation via autoregressive predictive updates.
Hi, I think that's me. Do you hear me?
Yes, we can hear you.
Yeah. Okay, amazing. Then, wait, are you sharing the slides already? I don't see. Should I share my slides?
We're running it off here, so just tell me when you need a next cue. So.
Oh yeah, the next. So amazing. Okay, amazing. Hi everyone, and thank you for joining the virtual spotlight. So I will present some work done in collaboration with colleagues from Oxford, Novo Nordisk, and UCL, and what we are doing is, I'll just go through the title. So we are taking a Quasi-Bayesian approach. That means we have a Bayesian model and we don't estimate it with variational inference or MCMC, how it's usually done, but we use, we cheat a little bit and like just change the functional form, which doesn't make it, Bayesian anymore, but we call it Quasi-Bayesian. Then we do non-parametric density estimation. So in Bayesian non-parametric density estimation, you usually use a Dirichlet process mixture model that you use to estimate some densities. And because we cheat and use a Quasi-Bayesian approach, what we get is autoregressive predictive updates. And what that is, I'll explain in the next slide. So Bayesian predictives are you get by assuming a Bayesian model, and then after observing I observations, you can compute the posterior after I observations, and with the likelihood and integrating it out, you get the Bayesian predictive after I observations. And we want Bayesian predictive updates, as I said earlier, and that means you have an online approach where you update your predictive after I-1 observations to the predictive after I observations. And we do that with function h. And in the next slide, I'll tell you how we get that function h. This is what makes our approach Quasi-Bayesian. So we assume that we just assume we have a prior and look how the first update looks like in a Bayesian model, and we repeat that first update over and over again by adjusting the learning rate a little bit and replacing our observation with the new observations. And this gives us an online approach that is faster than MCMC, but doesn't make assumptions like variation inference. So please look into our paper if you're interested in more.
All right, thank you. Next up, we have conditional counterfactual causal effect for individual attribution.
Okay, hi. Hi, everyone. My name is Ruiqi Zhao, and I will give the representation for our paper. At first, actually, identifying causes of an event, also termed as the causal attribution, is a commonly encountered task. Existing methods, for example, probability of necessity or positive CE, suffer from 2 main drawbacks, I think. The first is that they cannot attribute for individuals, and the other is that they only attribute for one single cause at a time and cannot deal with the interaction effects among multiple causes. So in this paper, we propose an individual causal attribution method called the conditional counterfactual causal effect. Next slide, please. Yes. So as shown in definition 1, we give the definition of the CCE, and this method can utilize the individual observation and the evidence, and is able to handle the common influence and the interaction effects. And it should be noted that the evidence set W may contain the variables XS and the outcome variable y. So the triple CE is actually a counterfactual quantity, and hence it needs several assumptions to identify this quantity. And here we give two assumptions, monotonicity and non-conformance, which are generalizations of conditions of post-TCE and PN or PS and so on. So based on this assumption, next slide, thank you. So based on these assumptions, we give the identifiability equations of triple CE, and as shown in this slide, especially theorem 2 give a general result, and we do the experiments on simulation or real data in our paper. Okay, thank you.
Thank you. The speaker's not online for this one. Okay, I guess we will skip one. Let me know if the speaker shows up. We can go backwards. Okay, so skipping one, up next we have multi-view graph contrastive learning for solving vehicle routing problems. We can't hear you. I don't know if you can unmute on your end. Okay, so in interest, we will move on. We can always go back. So up next, MFA, multi-layer feature-aware attack for object detection.
Okay, can you hear me?
Yes, we can hear you.
Oh, hello everyone. Now I will introduce the spotlights on my paper to you. The title is Multi-Layer Feature-Aware Attack for Object Detection. Oh, next slide, please. Oh, this is the structure of our method. Specifically, given a training set and a 3D model. Take a car, for example, the camouflage texture is rendered to the surface of the car using the natural renderer, which is differentiable. Next, we use a Ruiqi transformation function to transfer the camouflaged vehicle into the different Ruiqi scenarios and feed into the detector. Then we can obtain the importance of multi-layer features by backpropagating the ultimate outputs filtered by post-processing. Finally, the adversarial camouflage is updated through backpropagation with our device loss function. Okay, next slide, please. The total loss is a weighted sum of adversarial loss and smooth loss. Smooth loss ensures the smoothness of the generated adversarial camouflage. The adversarial loss devised by us use multi-scale features and the importance of features to detectors' outputs, minimizing the pixel level product, ensure the adversarial camouflage is generated in the opposite of the correction direction of the object detection task. Okay, that's all. Thank you.
Thanks. So up next, we have incentivizing diffusion while preserving differential privacy.
Can you hear me?
Yep, we can hear you.
Yeah, great. Thank you. Well, good afternoon, everyone. I'm Meng Xiao. I'm a research associate from the UESDC. I'm really glad to be here to share our study at the UAI 2023. Next, please. Well, diffusion auction is an is an emerging business paradigm of online social network commerce. Well, in a diffuser auction, a seller can utilize the power of social network to diffuse auction information by inviting friends, etc., to join the auction. In this way, the seller can attract a large number of potential buyers. On the other hand, most of the online users are concerned about their privacy issues. The bids in auctions are also private, as they often imply buyers' preferences and confidential business strategies. So in this paper, we focus on the privacy issues in diffuser auction, and we investigate how to design a differentially private diffusion mechanism that guarantees desirable incentive properties, that is IC and IR, and preserves bid privacy, that is ensuring the differential privacy for bids. Next, please. Well, we propose two mechanisms, and both of the mechanisms are based on the main idea of market division. We treat the whole social network as a whole market, and we partition the buyers into submarkets and associate the probability with each submarkets. Then the buyers in a submarket share the probabilities. And the one mechanism is recursive DPDM that treats its subtree as a submarket, while the other mechanism is layered DPDM, which treats each layer as a submarket. Both of these mechanisms have good properties, include the IC and IR and the differential privacy theoretically and also empirically. Next, please. Yeah. Thank you very much for listening. If you have any questions or if you are interested in our paper, please come to the room 325 or contact me at this email address. Thank you.
Okay, so it's me, right?
Yep. So residual-based error-bound for physics-informed neural networks. Take it away. We can hear you.
Yeah. Hello everyone. So the title is Residual-Based Error-Bound for Physics-Informed Neural Networks. Next one, please. So neural networks can be used to solve differential equations. The idea is that neural networks are universal function approximators, and the solutions to differential equations are just functions. So the way you train a neural network to solve a function is by defining the loss as the left-hand side subtracted by the right-hand side. If the residual is 0, then you have a solution. If it's not, you try to minimize it using a gradient descent. The advantages of this approach is that it's parameterizable because you can train once across many different setup of equations. For example, in a traditional method, if you tweak the initial condition by a tiny little bit, you have to retrain the whole thing, resolve the whole thing. But for neural networks, it's not a problem. And it's also have lower storage because it doesn't have to save a very dense mesh of values and do the interpolation. And the evaluation is very fast because you can have batch computation with GPUs. The drawbacks are that you have to do some empirical tuning and some empirical training. And also we don't know the error or the order of the error. So our work, what we do is we bound the error using the residual. The residual is basically the loss, the left-hand side subtracted by the right-hand side. And our work works for any neural network, even if you have a garbage randomly initialized network. And we also offer some trade-off between tightness and speed. So you can have faster algorithms that gives you looser bound and slower algorithm that gives you a tighter bound. Next, please. So to give you an idea of what we do is that, so consider a normal machine learning classifier. When you train, you use KL divergence. If the KL divergence is 0, then you know your accuracy is 100%. But if it's smaller than, let's say, a very small threshold, how good is your accuracy? In general, we don't know. So basically, in this case, KL divergence is like accuracy and residuals like error. We try to evaluate the error using accuracy. Yeah, so our algorithms work for the following set of equations listed here. If you have any questions, we can talk about it in the poster session tomorrow.
Thank you.
Okay, hello
next,
everyone.
have on the informativeness of supervision signals. We can hear you.
Hello, everyone. Fantastic. My name is Rory Battleday. I'll be speaking today on the informativeness of supervision signals, which I've done in collaboration with all these lovely people. Next slide, please. So our study is done in the context of supervised learning, in which you've collected a set of stimuli and you know, for instance, the number of classes that those stimuli fall into and the number of stimuli per class. And you want to answer the question of which kind of label should I use to supervise? So in this study, we conduct an analysis of the appropriateness of different labels in terms of representation learning. Representation learning being the learning of a low-dimensional latent structure for a set of high-dimensional stimuli. We answer the question in terms of how informative different labels types are for learning good representations. We conduct a theoretical analysis and we find three very interesting regimes. The first is that if the number of stimuli per classes is very high compared to the number of classes, one should prefer hard labels, at least if it's cheaper to collect them. So hard labels are the traditional one-shot, one-hot labels used in supervised learning. If, however, the number of stimuli is approximately 1 per class in the low-shot regime, or is fewer in the less than one-shot regime, then soft labels should be preferred. Next slide, please. But ultimately, the choice of which label you're going to use depends on the cost, how much it costs to gather each of these kind of label types, and also your utility function. And so the red arrow in each of these plots shows a particular data set in terms of the number of classes that are there and the number of stimuli per class. On the left, we have a couple of different utility functions in a high cost setting, and in the right, we have a couple in a low cost setting. Now, it really depends on what your choice of utility function is, but there are kind of three general findings. The first, roughly, is if the number of samples per class is small, or the number of classes are small, you should really prefer using soft labels. However, if the number of classes is high and the number of stimuli is high, per class is high, then preferred hard labels, or if soft labels are cheap, collect soft labels. We then do a range of classification experiments. Okay, I guess I was still on the last slide. Yeah, and so thank you. So here what we're doing is we're interpolating between the traditional hard label and a soft label. We're generating, decreasingly sparse soft labels. And we find this sweet spot in terms of the accuracy of networks trained on those labels, in which a particular amount of softness confers the best advantage to accuracy. Interestingly, what we find is that learning better representations, more closely approximating ground truth, results in more robust and better generalizable performance. So increasing distributional shift, use labels that are going to confer better representation learning. Thank you very much. And then on the next slide, I thank this lovely team of people I've had the chance to work with. I'll see you tomorrow at the poster.
Thank you. Any word on if we're going backwards? Okay, so I think that's the end of the first spotlights. Yes, all the posters will be there tomorrow. So note your questions and ask them then. Thank you all.